Am I audible? Hello. Am I audible? No. Thank you. So, I welcome you all to the week 4 live interaction session for the course on renewable energy engineering, solar, wind, and biomass energy system. Let's just wait for another 2-3 minutes. Let us give some time for others to join before we begin our session today. So I think we can start. Let me just share my screen. I hope my screen is visible. Anybody can they please let me know whether my screen is visible? Am I audible? Thank you so much. So I am Pratyumnan from the Department of Chemical Engineering. I am pursuing my PhD in the Department of Chemical Engineering at the Indian Institute of Technology, Guwahati. I am the course team member who is responsible for conducting the live interaction session for the course Renewable Energy Engineering, Solar, Wind and Biomass Energy System offered by Indian Institute of Technology, Guwahati. The course instructors for this course are Professor Vaibhav Vishant Gaud sir and Professor Ananda Lakshmi ma'am from the Department of Chemical Engineering, IIT Guwahati as well. So today we will actually start with the place where we ended last week. So if you remember, for the week 3 session, like which happened yesterday, we actually focused on solving the problems related to calculating the efficiency of the flat plate collector. So unfortunately, due to time constraints, we were unable to complete that problem. So first let us solve that problem before we move towards week 4, that is parabolic, cylindrical parabolic solar collectors. So let me just go to that particular slide, because since many were not present in the meeting yesterday, so they may not be able to really have an idea of what is happening. So this was the question which was taken up yesterday in the live interaction session. The question is that the flat plate collector is installed on a building rooftop in Mumbai at an angle of 30 degrees, which is actually the slope of the flat plate collector from the horizontal direction, pointing due south. So we are asked to calculate the respective values, that is solar angle, angle of incidence, tilt factors, and then the instantaneous beam and global radiation, instantaneous value of the total solar radiation incident on the flat plate collector. So this problem is particularly asking for to calculate the values on 16th August at 14 hours LAT. Suppose if you are given just like 2 hours or like 9:30 a.m., that is the solar time. So you have to actually convert the solar time to latent local apparent time. So if you remember, in week 1 we actually went through the calculation of how to convert solar time to local apparent time, that is where we involve about the equation of time correction, the b value, and then use the standard longitude and then get the local apparent time. So we discussed about the calculation of angle of incidence, which is something that we are repeating in week 1, week 2, as well as last week during the week 3 session also we calculated the angle of incidence once again. But here in week 1 and week 2, if you see, we primarily focused the location was New Delhi, and then the angle of the slope of the flat plate collector was around 45 degrees. So here we have just changed the location and then the slope of the flat plate collector, and we calculated the angle of incidence. Same, we calculated the declination angle and then we calculated the hour angle. So the declination angle was around 13.45 degrees and hour angle came around minus 30 degrees. Minus 30 degrees. The reason why it is minus is because the local apparent time is in the afternoon after 12 p.m. So in the evening we actually take the sign convention as negative. So we completed the calculation of angle of incidence as usual, like substituting the value of latitude and then declination angle, then beta is your slope of the flat plate collector, gamma which is your surface azimuthal angle, which is, since the flat plate collector is pointing due south, so the gamma value was 0, and then so after substituting the value we got the cos theta value as 0.782, and taking the inverse of that, taking cos inverse, we get the theta value as 38.56 degrees. After which we moved on towards calculating the zenith angle, and then since here we do not have the values of the beam global radiation, the intensity of the beam radiation and the intensity of the global radiation, so we calculated both of them using the beam normal, the intensity of the beam normal radiation. So using these relationship we calculated the values of A, B and C are taken from the literature, and here we converted the watt per meter square into kilojoule per meter square hour, and then we use these formulas like IB equals IBN cos theta z, where theta z is the zenith angle, and then we calculated the diffusive intensity of the diffusive radiation, and then the sum of the beam plus the diffusive radiation was the global radiation, that is the intensity of the global radiation. Then we calculated the tilt factors for their respective radiation, that is for the reflective radiation, diffusive radiation and beam radiation. The value of RB was, we calculated around 0.8991 RD and RR, and with this we calculated the total instantaneous value of the solar radiation that is falling on your flat plate collector, which came around 2883.24 kilojoule per meter square hour. So here the value of IT is an instantaneous value and not the average, like the monthly average daily radiation that we calculated during the week 1. We calculated at that time, if you remember, we calculated the monthly average daily global radiation, monthly average hourly global radiation, but these are the instantaneous values. Then we moved on towards understanding about, so here after calculating the angle of incidence, the sun rays is falling onto your glass cover. This glass, so when the beam radiation fall onto the glass cover, it undergoes refraction because it's going from the air medium to the glass medium. So we calculated the angle of refraction using Snell's law, where Ni sin theta equals to Nr sin theta r, and then we calculated the angle of refraction to be around 20.26 degrees. After calculating the refraction angle, now the sunbeam radiation is actually going to pass through the air that is filled between your glass and the absorber plate. So we calculated the two polarization components due to reflection and refraction, rho 1 and rho 2, and then we calculated the transmissivity due to reflection and refraction components tau r1 and tau r2, and we also discussed why here the value is here we have actually multiplied the value as 2 into 2. We also discussed why the value of here it is plus 31, whereas in case of the other formula that was discussed during the video lecture, it was just written, if you see in the denominator, it was only 1 plus rho 1, but here we have taken the value as 1 plus 3 rho 1. The major reason is because of the number of glass covers that we are using. In the example problem that was solved in the video lecture, over there the number of covers that was used for the flat plate collector system was 1, but here we are using two glass covers. So here what actually we have is one glass cover, beneath that you have another glass cover, beneath that you have your absorber plate, beneath that you have your fluid tubes, which is actually having that fluid which will carry the heat energy and then use it for other application purpose like solar heating, room heating, space cooling, and many other applications like the desired ones for the flat plate collector, because the flat plate collector can be used only for low or medium temperature applications. Then we calculated the transmissivity due to absorption using the Boyer's law, that is e power minus k delta c divided by cos theta r, where theta r is your angle of refraction, k is your extinction coefficient of the glass. Here we have actually multiplied with the 2 because we have two glass covers. And then we calculated the tau alpha product, that is transmissivity absorptivity product based on the beam radiation, that is equal to tau alpha p divided by 1 minus alpha p into rho d. Here we have taken the rho d is your diffusive reflectivity and the value is actually taken it as 0.2. So this value is actually fixed. So you are supposed to remember this value, that is rho d can be calculated. Rho d, the formula for calculating rho d is tau alpha into 1 minus tau r, but since it's a diffusive reflectivity and we consider that it has a particular component, like the diffusive radiation actually is due to the scattering of the sunbeam radiation by the atmosphere. So you will have the diffusive radiation at each and every angle. So here we take a particular component as theta is 60 and based on that we calculate the diffusive reflectivity and the value is around 0.2. So the transmissivity absorptivity product for the beam radiation was calculated around 0.663. Now this is only for beam radiation, but in case of flat plate collector we also account for the diffusive radiation because they are also falling onto a flat plate collector and their contribution should also be accounted. So here we actually repeat the calculation of theta I with the 60. So as I said, diffusive radiation, since the sunbeam radiation gets scattered by the atmosphere, so the diffusive radiation are in all the direction. So we cannot keep accounting for every single radiation that gets diffused. So we take the theta is 60, which is the standard, and then we calculate the angle of refraction, which comes around 28.75. Similar methodology of what we used to calculate for the beam radiation. Here we took theta as 38.56. The reason is because our angle of incidence, that is the angle at which the solar beam radiation falls on the flat plate collector, was 38.56. So here we use the incident angle as 38.56. Now here for diffusive radiation, since there are multiple diffusive radiation, we take a particular component which has a theta I of 60, which is the standard, and then we calculate the angle of refraction. Similar, Ni sin theta I equal to Nr sin theta R, and then the value was around 28.75. Like if you have calculator with you right now, you can also calculate and then check it. It could be a practice problem for everybody. Like, you know, you can actually get to know how to really calculate, because here since there are many formulas with square and theta r minus theta I, there are chances that the value, you can actually do mistakes while calculating the values. So rho 1 and rho 2 values were calculated as 0.269 and 1.753 into 10 power minus 4, and then tau r1 similarly was calculated as it is here, 1 minus rho 1 divided by 1 plus 3 rho 1. That values were calculated, tau r1 and tau r2, that is transmissivity due to reflection and refraction. And then the tau r value was calculated, that is tau r1 plus tau r2 by 2. Then the transmissivity due to absorption was calculated as 0.934, and then the total transmissivity, that is from the contribution both of reflection and refraction as well as that of the absorption, was calculated around 0.6560. After which we used the same formula for calculating the transmissivity absorptivity product based on diffusive radiation, that is tau alpha p, similar formula, tau alpha p divided by 1 minus alpha p into rho d. Alpha p is your absorptivity of the plate, and this data is given in the question. Plate absorptivity and emissivity for solar radiation is 0.95. So that is substituted here, and then your tau alpha d value will come around 0.6294. So if you substitute all this value, that is tau alpha b and tau alpha d, in this equation, here your S is nothing but the solar flux that is absorbed by your flat plate collector. And we have seen in the design equations when we discussed in the class what is the equation that we use for calculating the solar flux incident onto absorbed by your flat plate collector, that is nothing but IBRB tau alpha b plus IDRD times RR, that is the tilt factors for the reflective radiation into IB plus ID, that is nothing but your global radiation. The sum of the beam plus diffusive radiation is nothing but the intensity of the global radiation times tau alpha d. The value is around 1953.486. So if you see that IT value, if you convert that also into watt per meter square, and then if you see the S value, both are not the same. That's what was discussed in the last class. It's not necessary that what radiation falls on your flat plate collector will be absorbed by the flat plate collector due to multiple reasons. One is due to the losses that happens within the system, and then other kind of geometric constraints decreases the value of the solar flux absorbed by the flat plate collector, by your absorber plate in the flat plate collector, because of the convection losses, re-radiation losses that happens when it goes from the cover to the absorber plate. So if you see like in this diagram of week 2, if you see here, your solar radiation is falling onto the glass cover, and then the refracted radiation move through the air, the space between the glass cover and your absorber plate is filled with air. So it gets refracted and then it moves through the air. So when it moves through the air, there are convective as well as that of the radiation losses that happens. So because of that, there will be some amount of the energy will be decreased. So your S value, so your S value and your IT value need not be always the same. After discussing this, we come to today's session, like week 4 session, where we will be solving how to calculate the efficiency of your flat plate collector. So do let me know in case if you have any doubts till now, like any doubts in the calculation, or because these calculations are quite, as I said previously also, these calculations are quite tedious and the probability of making a mistake in these calculations could be, the chances are quite high. So if in case if you have any doubts, then do let me know now, so that before proceeding towards calculating the efficiency of the flat plate collector, we can rectify, rectify if there is any queries from your side. So then in case if there are no doubts, then let us move for the week 4 session, where we will be solving the third part of that question that we took yesterday on flat plate collector, calculating the efficiency of the flat plate collector. So these are the details. So here you have first the absorber plate, then you have the collector, and then the collector tubes. So here the specifications are given, like length of the absorber plate, width of the absorber plate, thermal conductivity, thickness, and then in case of the collector, your insulation thermal conductivity, thermal insulation thickness. Because after the tube, the entire system, actually if you see for the flat plate collector, is supported by a support system, as well as there is a thermal insulation, so that whatever radiation that comes to the tube does not get, like the radiation that falls on the flat plate collector gets conserved within the flat plate collector, and not just that it gets radiated out to the environment. So because of which we have a thermal insulation at the bottom, so that the solar energy that falls on the flat plate collector is harnessed for our application, and it does not actually radiates out to the environment. If in case if that happens, the efficiency, the useful heat gained by our flat plate collector will be very less, and your efficiency in turn will be very less, and there will be no meaning for installing a flat plate collector. So that's the reason we have a thermal insulation with the insulation thermal conductivity here given as 0.04 watt per meter Kelvin. If you can see the difference in the thermal conductivity here. For the selective absorber plate, in order to increase the absorption of the solar radiation, the thermal conductivity is around 348 watt per meter Kelvin, so that a higher amount of the heat can be conducted. But to prevent the heat losses, the insulation thermal conductivity is around 0.04, that is extremely very negligible thermal conductivity. So much amount of the heat whatever is absorbed by the flat plate collector will be used for your application. And then here you have the collector tubes, the fluid tubes, the tubes in which the fluid is filled, which will take up the heat, which will take up your heat and then use it up for your other applications like space cooling or space heating or crop drying or domestic, any kind of domestic purposes. For that heat will be used up. So here you have the inner outer tube diameter, and then the tube center to center distance, and then inlet temperature is nothing but the inlet temperature of the liquid that is going to flow through the tubes. So here we take the temperature as 60 degrees Celsius, and then other miscellaneous details are that ambient air temperature is at 25 degrees Celsius, mass flow rate of the water through the tube is maintained at 100 kg per hour, and then US is nothing but 10% of UV. This we will see later when we actually calculate the loss coefficients. So before moving on towards calculating the efficiency of the flat plate collector, let us just go through once again what we discussed in week 2 about the heat removal factor, collector efficiency factor, and the plate effectiveness factor, because this problem actually starts here. So your Fr is the heat removal factor, which is given by m dot Cp divided by UL AP into 1 minus exponential of this term, where F dash is your collector efficiency factor, and your here F dash is again nothing but is a function of your phi, which is called as the plate effectiveness factor, that is with what effectiveness your absorber plate is going to absorb the heat. And then here if you see, you have a term called W. This W is nothing but it is called as the pitch of the tube. So the pitch is nothing but it is defined as the distance between the two centers of the tube. If you see this figure, these are the two centers, and the distance between the two centers of the tube is nothing but called as the pitch of the tube. And then we calculate the loss coefficient, which is nothing but the sum of the upper, bottom as well as the side. So if you remember what we saw in that picture which we discussed just now, so here if you see, you will have the loss of heat that is happening through all the three sides. One is through upper side because of the re-radiation and the convection losses, and one will be towards the side of the flat plate collector, and then the other one will be through the bottom of your flat plate collector. So when you measure the loss coefficient, you have to account for all the three different kinds of loss coefficients, that is the loss coefficient through the upper part of your flat plate collector, through the sides of your flat plate collector, and through the bottom of your flat plate collector. With this also we will be calculating towards the end of this particular class today. And then we at the end we calculate the efficiency. Efficiency is nothing but the useful heat that can be used up, that is the heat that the fluid actually takes with it for its application to the total amount of heat that is absorbed or falling onto the plate. So which is given by Qu divided by S times AP. AP is nothing but your area of the plate. So in case of the flat plate collector, since it's a non-concentrating collector, your absorber as well as that your plate area both will be the same, like there is no kind of a concentrator that is involved. So let us actually move towards solving the problem. So first, if you see here, in order to calculate your heat removal factor, you need to know F dash, because your heat removal factor is a function of your collector efficiency factor, which is in turn is a function of your plate effectiveness factor. So first let us here calculate the plate effectiveness factor and then move towards collector efficiency, and then finally we will solve for Fr. So here you can see the formula. So phi is nothing but tan h of m into W minus D naught by 2 divided by m into W minus D naught by 2. What is your m? M is nothing but UL divided by Kp delta P. Kp is the thermal conductivity of the plate, and your delta P is nothing but your plate thickness. So here if you see in the details, your thermal conductivity of the selective absorber plate is nothing but 348 watt per meter Kelvin, and your thickness, that is the delta P value, is 2 millimeters. So here you need to be cautious about the units. In the entire problem you have to be cautious about the units because they have to be consistent with the SI units. Since the thickness is usually very small, we express here it in mm, but when you take it for your calculation purpose, you are supposed to convert your millimeter scale into meter scale and then use it for the calculation. So this is your value of m. So here we initially, for the problem's sake, since the loss coefficient is not actually just a minute. Okay, let me just, can you see my slides now? Is it like I'm scrolling through my slides? Oh. Now? Oh, okay, just a second. What about now? Like I have zoomed in. Is it visible now or is it still not? Yes, can anybody know whether the slide is visible or it's still stuck at one place? Oh, okay. Okay, let me do one thing. Let me just stop presenting and reshare my screen once again. Now is it visible? Oh, okay. Just let me know whether it's visible in the PowerPoint mode or shall I proceed with this zoomed version of the PPT. Okay. So yeah, so let me just, I guess, repeat what I said previously also. So if you see, here we start the problem with the calculation of your plate effectiveness factor, and here your plate effectiveness factor is nothing but is a function of pitch of the tube and then d naught and your m, where m is nothing but ul divided by kp delta p whole power 0.5. So your ul is nothing but is the loss coefficient, kp is the thermal conductivity of the plate, and delta p is the thickness of the plate. So kp is value, as we have seen from that slide where we have the details, the specification about the absorber plate, the value of kp was around 348 and delta p is around 2 millimeter. So ul, since it is not given to us in the question, we assume the value, initially we assume the value of ul as 4 4 meter square per degree Celsius or 4 watt per meter square Kelvin. So both will be the same because the units are all is the same as temperature. So degree Celsius and Kelvin will not make much difference. So here we calculate the value of m. So m, so 4 divided by 2 into 10 power minus 3 into 348. So that will be around 5.74. Let's just calculate that once. So 4 divided by 348 into 0.002. Yeah, So the value of your m will be around 5.74, but let me just check whether if there is any kind of mathematical error. So these are the chances where you can actually make the errors. Yeah, it's fine, it's correct. M is 5.74. So now you have to calculate the m into W minus D naught by 2. So D naught is nothing but the outer diameter of your tube, so which is 0.018. Oh, see here the data is actually so because outer diameter will always be more compared to a inner diameter. So outer diameter of your tube is 0.018 and inner tube diameter is 0.010. And do we require any other value? We need to know the tube center to center distance, that is 0.12 meter, that is the pitch of your tube, as I said previously. So that value is around, so if you calculate, that value comes around 0.292. So now you can actually calculate the plate effectiveness factor, that is nothing but tan h of 0.292 by divided by 0.292, which will be 0.972. So your plate effectiveness factor is 0.972. Since now you know your plate effectiveness factor, the value of your plate effectiveness, you can calculate the heat removal factor. The collector efficiency factor. So again, this is all it's about substitution, and so if you see the formula, let me just show you the formula, and then we'll just see what are the terms, and depending upon that we can actually substitute. So your f dash is nothing but 1 divided by W. W is the pitch of the tube, so that is that value is 0.12 meter. UL is your heat loss coefficient, so which we assumed as 4, and then here you have your phi, that is the plate effectiveness factor which we got. D naught is nothing but your outer diameter of the tube, and here this lambda A divided by Ka delta A is nothing but your adhesion resistance, and your adhesion resistance in majority of the question will be 0. So that particular term will be 0, and here you have 1 divided by pi di hf. Hf is nothing but your heat transfer coefficient. So when the fluid is going to take up the heat, it will have a particular heat transfer coefficient. So the heat has to be transferred from the absorber plate to the fluid. So due to which there will be a heat transfer coefficient term associated with that, and your di is nothing but inner diameter of the tube. So if you substitute all the value as it is given in the question and then calculate, your value, your f dash value will be around 0.8186. You can also calculate and check to verify whether the value is 0.8186. And then we calculate the heat removal factor after that, because now we know phi. After phi we calculated the collector efficiency, and now we know your heat removal factor. That is nothing but m dot Cp divided by UL AP into 1 minus e power minus f dash UL AP by m dot Cp. So here your m dot is nothing but the mass flow rate of the fluid that is going through your tube, which is expressed in kg per hour. So if you see the question, our mass flow rate is nothing but 100 kg per hour. UL is your assumed loss coefficient. AP is the area of the plate, which is nothing but the length of the collector plate and the width of the absorber plate. Let me just show. This one. So length into width is nothing but your area of the absorber plate. Here we assume that our absorber plate is rectangle in shape. So 1.5 times 1. So if you calculate this value, what you are going to get is 14.51. So you know m dot Cp by UL AP. So this is just nothing but the f dash times inverse of this term. So if you just multiply all these things, what you are going to get FR value as 0.796. Let's just try calculating. So e power minus 0.8186 divided by 14.51 e power minus 0.056. E power of that is, let me just calculate this, e power of minus, okay, let me just calculate using my calculator and I'll let you know the value. E power minus 0.056, that is 0.94 into minus 1 will be okay. The value is 0.945. So e power minus 0.056 is 0.945 into minus 1. So let's just assume it as 1 minus 0.945. This into 14.51, that is 0.798, 0.796 FR value. It all depends upon how many decimal places you actually take. If you see, even in this week 3 assignment questions, for which you already have the answer keys, especially for the second question, there have been a lot of queries stating that the values are actually not really matching with the options. But the main problem what is actually happening is that you need to actually take up to 4 or 5 decimal places and then calculate your values. If you do that, then your values, that is the transmissivity absorptivity product, will be matching with the options given. So it is better for these kind of questions to take up to 4 decimal places and then solve. So if you do take up 4 decimal places and then solve, your value will be 0.796. Since here I have taken, I guess, 0.945, and then just for for the practice, here we are calculating, the value came around 0.798. So that's not a much big difference. So now we have calculated FR. So this is one of the term which we had to calculate the amount of useful heat gained in the system. So QU is nothing but FR times AP times S minus UL into T in minus TA. So your FR is 0.796, AP is 1.5, your S, that is the solar flux that is incident onto your flat plate, absorbed by the flat plate collector, is 1953.486, UL is 4, T in is nothing but the inlet temperature of the fluid, and TA is nothing but your ambient temperature. So here we are taking the ambient temperature to be 25 degrees Celsius or 298 Kelvin. Here it won't make much difference even if you express it in Kelvin or degree Celsius, because that plus 273 factor will be a constant. So it is like same, it will be 60 minus 25, and then if you add 273 on both the sides, that subtraction sign, that 273 and 273 will get subtracted. So at the end you will be getting only 35 as your delta T. So if you calculate this, what you are going to get your U is 2165 times 302 watts. Here it won't be watt per meter square because you are multiplying your S with the AP. So that meter square and meter square will get cancelled. So your QU will be 2165.302 watts. If we want, let's just calculate this also. 4 into 35, 140, and 1953.386 minus 140, this into 1.5 into 0.796, somewhere around 193, 2165.302 watts. That's what even we got here. So this is your useful heat gain, that is, this will be the heat gained by the fluid which will be actually used for your application. You can actually see the difference between your ITS and QU. How much initially was the value and how much value it got reduced to. So that's why in case of the flat plate collector, if you see compared to parabolic collector, flat plate collector, the efficiency will be less. Like the amount of solar radiation that gets absorbed by your flat plate collector and which is in turn used for your application will be significantly reduced. Now we have calculated QU, let's calculate QL. QL is nothing but APS minus QU. The reason why we calculate the value of QL is to know what is your mean plate temperature, that is the temperature of your absorber plate. So QL is nothing but AP times S, that is area of the plate, times your solar flux that is absorbed by your flat plate collector, minus the useful heat gain. So it makes sense. What this expression means is some amount of the heat, so some amount of the heat actually falls on your flat plate collector which gets absorbed by your flat plate collector, that is your SAP. This SAP again falls on the absorber plate, but out of which a portion of this energy is actually taken up by your fluid. So the rest amount of heat that is actually there present will be used to heat up the part of the energy that actually is absorbed by your flat plate collector will be used to heat up your absorber plate. Once your absorber plate gets heated up, that energy will be used by your fluids for that energy will be used up to heat up your fluid which will be used for your application. So that amount of energy that is absorbed by your absorber plate is QL. So APS minus QU. So here you can see the amount of energy that is absorbed by your absorber plate is 764.972 watts. So that's what I said. You can actually compare how much it gets absorbed and how much is actually getting used up by your fluids for your application. So the difference in the amount absorbed and the amount of heat that is gained by your fluid is 764.972 watts. So this much amount of heat is actually required to heat your flat plate collector, heat your absorber plate, which will then heat up your fluid. So this QL also can be represented as UL times AP times TPM minus TA. TPM is nothing but your mean plate temperature. So you have the absorber plate. For that plate you need to calculate what is the temperature of that plate. So the temperature of that plate will be 764 minus 0.972 divided by 4 into 1.5 plus TA. TA is nothing but your ambient temperature, that is 25 degrees Celsius. So what will be the value? Can anybody tell me what will be the value of TPM? And I hope there are no, and I hope if in case if you have any questions, then do let me know either in your chat box or by unmuting yourself. And I hope the slide is also visible now. So calculating the value of TPM, let me just show keep that slide. It's just division, so you will be able to do. But the concept is that particular amount of heat energy, that is your 764.972, will be used up to heat your absorber plate. Anybody with an answer? It's very simple. Let me also calculate here. 764.962 divided by 6 plus 25. That is approximately 152.49 kcal. 436 or 495, and this plus 273. Let us express it in terms of both Kelvin as well as degree Celsius, because in case if anywhere it requires you to use Kelvin, then we can use Kelvin there. 425.49. I guess 4 or 39 degrees Celsius, or how much was it? 425.49 Kelvin. So this is the absorber plate mean temperature, that is the mean plate temperature of your absorber plate, in other words. But the main thing is the expression. What does the expression actually mean? The QL is your heat taken up by your absorber plate, which is nothing but it's basically the amount of energy that is absorbed minus the amount of energy that is gained by the fluid. Now we know the mean plate temperature, the amount of energy that is absorbed by your absorber plate. We have to actually calculate the heat transfer coefficient. So here we will be specifically focusing on how to calculate the heat transfer coefficient. The main reason why this is actually being done is, here we have assumed our value of U, if you see, as 4, but there is no basis for this assumption. We do not really know whether this assumption is right or wrong. We have just assumed the UL as 4. So this is how you will do. You will not be knowing what is the heat loss coefficient. So you have to assume a particular value. Here we have assumed 4. You can assume anything that can be like 5 or your value, but within this range. And then you need to calculate the heat transfer coefficients, and then afterwards calculate the values of UU, UV as well as US, and then you should check whether that sum and then the value that you initially assume, that is UL as 4, whether they are matching. In case if they are not matching, then you have to do the reiteration. So that's what we are going to do. We are actually going to check whether the UL that we are getting at the end of our problem solving and the UL that we assumed at the start of the problem are same or not. In case if they are not same, then we have to change parameters in such a way that the values will be around the same. That is, your assumption value and the value that you are calculating should be almost or approximately be the same values. So how do we calculate the heat transfer coefficients? So this is the these are the equations. So here you can see actually some very complex equations with the numbers actually written. So let us actually see each and every formula separately before proceeding for solving the rest of the problems, because this will be more towards that of the heat transfer oriented calculation. So you will be focusing more on the thermal properties of the flat plate collector system. So this course is particularly designed in such a way that you basically focus more on the geometric design as well as this thermal design of the flat plate collector. There are also other kind of designing or modeling of the flat plate collector, like in terms of your material modeling. So the absorber plate that we use should be a selective surface and it should be coated, it should be black in color. The reason why it is black in color is because it will absorb all the radiation, all the wavelengths of radiation that falls on it, so that the temperature of your absorber plate will be high, so that as the temperature of your flat plate is high, if your delta T, that is the temperature between your absorber plate and between your fluid, if the difference is very high, then the amount of heat transferred will be more, and it will only take a very less amount of time for the heat transfer to happen. That delta T is a very important value, the temperature difference. Higher the temperature difference, faster will be the heat transfer happening. Yeah, that one. So so that is the reason. So this is one way of doing the material modeling. So what kind of different materials we can actually explore for the flat plate, for the absorber plate. Like that, you have the transparent glass cover. Can we use some other glass cover in, or some other material in such a way that we can trap almost all the solar radiation that comes into the system, but not let any of the radiation to go back to the atmosphere due to the convection and the radiation losses. Like, is there any possibility, do we have any material in such a way that we can minimize the convective and the radiation losses to a much greater extent than what it is actually present today? That is again another part of designing, but since this course is specifically focused towards this thermal properties and thermal analysis, so we do majority of the calculation based on heat transfer. So in case if you have any doubt till now, then please do let me know about what is this QL, TPM, heat removal factor, collector efficiency factor, because there are a lot of different terms which we have discussed today. So in case if you have any doubt, then please let me know now. I hope with what we actually saw as a recap in today's class of the previous session, there won't be any much doubt, hopefully, because that's just calculating angle of incidence and declination angle. And the week 3, if in case you have missed the session, then the YouTube link will be, the video will be uploaded in the YouTube soon, and you will be receiving the link, so you can always watch it there. But if you have any doubts in what we have discussed so far today in the 1 hour session, if you have any doubts, then please do let me know. So then, if nobody has doubt, let's just move on towards knowing how to calculate the heat transfer coefficients. So as from an engineering point of view, you actually need to know how to calculate the heat transfer coefficients, because if you have given a flat plate collector to model, you should be knowing the parameters. But from the exam point of view, these may come, but it may not be like an entire single problem. For example, if you see your week 3 assignment, the first 2 questions are what we actually discussed here also. Yesterday we discussed the same type of questions. It's just that we are actually continuing to solve so that we can know how to calculate the efficiency, because our ultimate goal is to calculate the efficiency of the flat plate collector. So from the engineering point of view, we need to know for any kind of system what is its efficiency. So with keeping that in mind, we are actually solving the problem, and it's big. So let's just go step by step again. So the heat transfer coefficient here, as I said previously also, the total number of covers that we have is 2. So you have your plate, the absorber plate, then cover 2, cover 1, and then comes your the atmosphere, that is after cover 1 is your atmosphere. So you will have totally to calculate 3 different types of coefficient: your HPC1, convective heat transfer coefficient between the plate and the cover 1, convective heat transfer coefficient between the cover 1 and cover 2, and the convective heat transfer coefficient between your cover 2 and the atmosphere. So here there is a mistake. I will change it in the PPT which will be uploaded probably by today or by Wednesday. This is not plate to cover 2, it is cover 1 to cover 2. there is a mistake here. So this will be rectified in the PPT, which will be uploaded in the portal soon. So here for plate and cover 1, that is the radiation is moving from plate to cover 1, that heat transfer coefficient between the plate and cover 1 is calculated as QT by AP is equal to HPC1 times T 425.5 is your TPM, that is your mean plate temperature, minus your temperature of cover 1 plus this is nothing but your solar constant 5.67 into 10 power minus 8 into this is again your TPM, the mean plate temperature of the absorber plate, 425.5 to the whole power 4 minus your TCI, that is your temperature of the cover 1, because we actually do not know what is the temperature. We know how much amount of the heat is falling onto your absorber plate, how much amount is getting collected by your absorber plate, that is absorbed by your flat plate collector, how much amount of the heat is actually gained by the fluids that is flowing through the tube. But we do not actually know what is the temperatures of the glass cover or and the plate which is present at the intermediate part of your system. So here we calculated the mean plate temperature. So first part is done. Now we need to know what is the temperature of your cover 1 and temperature of your cover 2. Also the heat transfer coefficients. We do not have an idea of what will be the heat transfer coefficients, HPC1, HCC1. So that also has to be calculated. And this 1 by 0.95 and 0.88 is nothing but your plate absorptivity and your plate emissivity. If you go here, you will be knowing. Oh, this was given in the previous question. Let's go to week 3 slide. If you see here, plate absorptivity and emissivity for solar radiation is 0.95. And your glass cover emissivity and absorptivity both, but over there those two terms of emissivity, plate emissivity and glass cover emissivity, so that is 0.88. So this is 0.95 and this is 0.88. Now we can calculate the values of QT by AP. So here you know, so that is 0.95 and 0.88 minus 1. This is the formula. If you want to know what is the exact formula, like in terms of the expression, like the formula expression, you can always go and check the video lectures, week number 9, lecture number 9 of week 3. So over there the formulas are actually written. Here I have not given, but in the PPT that will be uploaded, I will add the formulas also. So this is for cover 1, so, between plate and cover 1. Here you can see the reason why I have given the emissivity of the plate and emissivity of the cover, these two values are different, but in case of cover 1 and cover 2 the emissivity is the same. So because this is between plate and cover 1 and this is between cover 1 and cover 2, that is the reason. So here so now we will see for cover 1 and cover 2, between cover 1 and cover 2 what will be the what is the heat transfer coefficient. So QT by AP is nothing but HC1C2 into TC1 minus TC2. Here we do not know the temperature of both the cover 1 as well as cover 2, and we do not know the heat transfer coefficient between cover 1 and cover 2. Both are, all the three are variables to us, so we do not have any idea. because you cannot actually measure and check, or you probably require some kind of a measuring system to measure the temperature of the covers which is present inside your flat plate collector. So that value is usually not given to us. We need to find out how to calculate Tc1, Tc2, and same 5.67 into Tc1 whole power 4 minus Tc2 whole power 4 divided by 1 by 0.88 plus 1 by 0.88. The reason, as I said, why it is both the emissivity is same, because this is between cover 1 and cover 2. And sorry, now after the cover 2, what you have is the atmosphere. You can always take it in the reverse way also, because since the solar radiation is falling on the glass on the cover 2, then cover 1, and then the absorber plate, so it's just that the order is going to change. So here the value of Qt by AP is nothing but HU, that is the heat transfer coefficient between your cover 2 to atmosphere. Now the radiation is between your atmosphere and cover 2 times Tc2, that is the temperature of your cover 2, minus 298. The 298 is your ambient temperature, 25 degrees Celsius. So here it is represented in terms of Kelvin, 298 plus 5.67 into 10 power minus 8 into emissivity of your cover 2 times Tc2 whole power 4 minus 292 whole power 4. The reason why here we use 292 is because these radiation will be moving towards the sky. So the heat transfer is between the sky as well as that of your cover 2. So the sky temperature is usually taken as T ambient minus 6. This is by convention we take T sky as Ta minus 6. So your T sky now will be Ta, which is 25 degrees Celsius or 298 Kelvin minus 6. So that will be equal to 292 Kelvin, and that is what we actually use here. So the beam radiation will actually come from your atmosphere, from the sky. So the temperature of your sky is 6 degrees lesser than your ambient temperature. So T sky is maintained as 298 minus 6, that is 292 Kelvin. So these are the three expressions for calculating the value of Tc1, Tc2, Hc1, Hpc1, Hc1c2, Hu and Qtap. So we have so many variables here. Qtap is 1, Hpc1, Hc1c2, Hu, Tc1, Tc2. I guess we have totally 6 variables but only 3 equations to solve. So let us see how to calculate the values in the next slide. So now we are supposed to calculate the heat transfer coefficients between the plate and cover 1 and cover 2, and when the radiation is in the from the atmosphere to your cover 2. So in order to calculate that, you need to know about, so here it is just given, you need to know how to calculate the Rayleigh factor, and once you calculate the Rayleigh factor, you have to use that to calculate your Nusselt number. You have to use this correlation. Even in the video lectures also, if you see that example problem that was solved uses these particular equations, RAL cos beta. So after calculating the value of Rayleigh number, you have to multiply that with your cos beta, and then you have to check the range. Once you know the range, you have to calculate your Nusselt number. Nusselt number is nothing but the heat transfer coefficient times the length or your thickness of your the spacing between your plate and cover divided by your thermal conductivity. Once you know that, you can calculate your HPC. Similarly, you have to do for Hc1c2 and then your Hu also. So let's see how to calculate. So this will be quite, again, as I said, these are very these are very complicated calculations, so you need to be kind of, if you solve parallelly, then it will be very helpful, because these terms are new, and we do not really have much understanding about, at the present moment we do not have much understanding. So let's just see how to calculate this. So if you see your Rayleigh number, RAL, so Rayleigh number is something that is associated when you have a natural convection that is happening. That is nothing but is equal to G times beta T times delta T into sigma Pc whole cube divided by V into alpha. It's nu into alpha. Here this alpha is nothing but, it's called as thermal diffusivity, and the other one is called as momentum diffusivity. Thermal diffusivity E is nothing but how much amount of the heat will be diffused through a particular material. Suppose you have a material, how much amount of the heat will diffuse through your material. That particular yes, does anybody have any doubt? I hope no. Okay, let me just continue then. Yeah, so that the amount of heat that gets diffused through your material is represented by the term alpha called thermal diffusivity. So beta T is nothing but 1 by T average. Now what is the T average here? Before calculating this, you need to assume something. So when you have to calculate all these things, your mean temperature, so the heat transfer is between your cover 2 and your flat plate and your absorber plate, but unfortunately you do not have an idea of what is Tc1 and Tc2. So for that also we actually make an assumption here. We assume here what is the value of Tc1 and Tc2. So just a minute. We take Tc1 as 360 Kelvin and Tc2 as 340 Kelvin. This is the assumption that we are going to make. So totally, for solving these kind of problems, we have to make 3 assumptions at the first itself. We have to make 3 assumptions at first. One is your UL, that is your loss coefficient in the flat plate collector system. That value is assumed. Now we are also assuming your temperature of the covers, that of the transparent glass cover used in your flat plate collector. Since you do not have the provision to know the values of Tc1 and Tc2, we actually make these assumptions here. Oh, sorry. So here we have taken our Tc1 as 360 Kelvin and our Tp is at a temperature 425. Let's take the mean of that. So mean will be 425.5 plus 360 divided by 2. 392.75. This is your mean temperature. With respect to this only we are going to calculate your Rayleigh number. So beta T is nothing but 1 by T average or 1 by T mean, which is nothing but 1 by 392.75, which will be approximately 0.0025. Since there is already denominators that are there, I am just going to leave it as 1 by 392.75. So G is nothing but it's your gravitational constant 9.8 or 9.81. Beta T is 1 by T average, so we keep it as 1 by 392.75 times your delta T. Yeah, delta T is nothing but the temperature difference between your absorber plate and your cover 1 temperature. So because the heat transfer is happening there only between your cover 1, and here we are specifically focusing for the time being the heat transfer that is happening between your absorber plate and your cover 1. So we have to take the delta T should be between your T of the absorber plate and T of the glass cover. So which is 425.5 minus 360, and your delta PC, that is the spacing between the absorber plate and your cover, which is 0.02 the whole cube, the cube. Now we have to calculate the V as well as alpha, that is your momentum diffusivity and your thermal diffusivity. So this momentum diffusivity and thermal diffusivity are temperature dependent. So their values actually vary depending upon your temperature. So in chemical engineering we actually do this. So depending upon the temperature we calculate the value of momentum diffusivity and thermal diffusivity. So how do you calculate this? So I hope everybody is actually able to see the table, that is how the variation of K, V as well as alpha, that is your thermal conductivity, momentum diffusivity and your thermal diffusivity based on the temperature of your temperature. So here we have many temperature, like 4 different temperature, 250, 300, 350 and 400 degrees Celsius, and depending upon the temperature we have your thermal conductivity, momentum diffusivity and thermal diffusivity values. So from here you are supposed to calculate the value of mu and your momentum diffusivity and thermal diffusivity. Those value will be around 21.788 into 10 power minus 6 and 0.31384 into 10 power minus 4. How do you actually get these values is you have to kind of do an interpolation. You have to extrapolate the values and then you have to get, like, you have to assume that the variation of thermal diffusivity, momentum diffusivity and your thermal conductivity is a linear function of your temperature, and then from there you are supposed to calculate the values of calculate all the three values. Let's just check for one. I'll just say how to solve this. So here we are assuming that your all the three parameters are a linear function of your temperature. So in that case the slope will be same. You can actually calculate the slope. So we take 309. So here we take 400 minus 392.75 divided by 400 minus 350. Let me just write this. These are quite complicated, and so let's just see how we are going to solve this, how we are supposed to solve this. 400 minus 392.5 divide, here we have to take the average temperature. Based on the average temperature only we are supposed to calculate the thermal and momentum diffusivity, divided by 400 minus 350. This is equal to, now we take their respective values. Since we have assumed that it's a linear function, their slope will be same, so we can take advantage of that particular assumption that it's a linear function. We do not know, again this is an assumption, we do not know whether it's actually a linear function of your temperature. So let's just see for thermal diffusivity alone. So that is for 400 the value is 0.3760 into 10 power minus 4. Since everything is here is in the order of 10 power minus 4, I am just going to write the I am just going to neglect the exponent value and then just the absolute value I am going to write. So 0.3760 minus, you do not know what is your thermal diffusivity at the temperature 392.5 Kelvin. So let's just assume that as x, and then similarly it's written 400 minus 350. So at 400, 0.3760 minus at 350. At 350 your thermal diffusivity is 0.2983. So this is the equation. So we are assuming, so I am again saying this, we are assuming that your all the three parameters, thermal conductivity, momentum diffusivity and thermal diffusivity is a linear function of the temperature. So in that case it will be a straight line. So it will be a straight line with a particular slope. So by knowing the slope we can actually calculate the thermal diffusivity at whatever temperature we want. Let's say if it is at here, if it is not 392.5, let's say it is 360, then we just plug in the value 360 here. If it is, suppose let's say you have a temperature of about 320 degrees Celsius, so your temperature 320 degrees Celsius, you can actually plug it in here and then you can calculate. Or this is one way, or if not you can actually change here. So you can also calculate, since 320 lies between 300 and 350, you can also write here as 350 minus 320 divided by 350 minus 300. So we are assuming that it's a linear function. So since we have made that assumption it's a linear function, we can easily calculate the value of any of the three parameters at any particular temperature of our interest. So now let's just move back to what we actually wanted to solve. So it will be 400 minus 392.75 divided by 400 minus 350. That's what we have actually taken. So if you calculate, so it's just taking it to that side. So it will be around 400, let me just do it here, 400 minus 392.75 divided by 400 minus 350, that will be 0.145. So let us write 0.145 times this 0.3760 minus 0.2983 is equal to 0.3760 minus x. Now you can calculate the value of x, that is the thermal diffusivity at the temperature 392.75 degrees Celsius as 0.145 times 0.3760 minus 0.2983. So it's 0.3760 minus 0.154 into 0.3760 minus 0.2983. If you do this, you will calculate the value of any value. Now it's not just that it's the thermal diffusivity, but all the values using this particular assumption we can calculate for any particular temperature. If we have the data for any particular intermediate temperature, we can know what is the value of thermal conductivity, momentum diffusivity as well as thermal diffusivity. So that is what we have calculated here, the value of alpha, value of momentum diffusivity nu. So now if you calculate this entire expression, your Rayleigh number will be approximately 19,121.215. Now you have to check. So you know the value of RAL. Let's calculate the value of RAL cos beta, or if you guys want, you can let me know. Yes, that would be best. Please let me know what is the value of RAL cos beta. It's simple. RAL value is known, 19121.21599. Cos beta is cos 30. So that would be around 19121.21599 into cos 30. Cos 30 will be root 3 by 2, that is 0.866. 16,558.97. So that will be approximately in the third range if you see. So this one. So this particular term Nu is, that is your Nusselt number, is equal to 0.229 times RAL cos beta to the whole power 0.252. So we have to use this expression. So these will be given to you because these are correlations. So these are derived from literature after many experimental findings. We have got the value, we have got the relationship for Nu as a function of RAL cos beta. So from here you can actually calculate the value of Nu, that is your Nusselt number. So RAL, you know, 1921.2159 cos 30 to the whole power 0.252. So your Nusselt number comes around 2.64. Now you know your Nusselt number. So if you know your Nusselt number, you can calculate the value of heat transfer coefficient between the plate and cover 1. So that is nothing but Nu K, the thermal conductivity, divided by delta Pc. Delta Pc is nothing but your spacing between the plate and the cover, that is 0.02. So Nu is 2.64, and then K, the thermal conductivity, again we have to calculate based on this data that is given, based on this expression, based on this way of solving. We need to calculate the value of thermal conductivity at 392.75 degrees Celsius, which will come around 0.03075. So if you calculate this, you will be getting divided by 4.059 watt per meter square Kelvin. So now you know what is the heat transfer coefficient between the plate and cover 1. Similarly, you have to calculate the heat transfer coefficient between cover 1 and cover 2. Same, you have to calculate your mean temperature. After calculating your mean temperature, you need to get the value of your Rayleigh number. Once you get to know the Rayleigh number by finding what will be your thermal diffusivity and momentum diffusivity, you will be able to calculate RAL Rayleigh number. Once you know Rayleigh number, you can get the value of RALB cos theta, and then using these 4 correlations, check where will be the value of RAL cos beta lie around, like in what particular range is your RAL cos beta, the value coming. Once you get to know what is in which particular range is your RAL cos beta lies, you will be able to get the expression for your Nusselt number. Once you get to know the expression for your Nusselt number, you can calculate its value. Similarly, once you know your Nusselt number value, you can calculate your heat transfer coefficient, that would be around 2.8205. So once you know the HPC1 and HC1C2, you can calculate the value of QTAP, because QTAP is a function of here HPC1 and TC1. Now TC1 we have assumed as 360 Kelvin, HPC1 we have calculated. So if you plug in those two values in this particular expression, you can calculate the value of QT by AP. QT is nothing but the total amount of the heat that is taken up by your flat plate collector system. So that is around 1028.05 in this case, and here it is 209.3412 watt per meter square. Now comes your last particular what do you call the system, that is between your cover 2 and your atmosphere. So that is usually given by the expression HU is equal to 5.7 plus 3.8 into V. V is your wind speed. Let me write here. H is nothing but H is equal to 5.7 plus 3.8 times V. V is nothing but your speed, wind speed. Here we have taken wind speed as 3 meter per second. Here V is equal to, please be careful when you are solving, especially make sure that all the parameters are in their SI units. So 3 meter per second, so that value will be 17.1. So you know HU, so you can again as such similarly you can plug it in this particular equation. Where is it? Between cover 2 and atmosphere, HU is known, Tc2 we have assumed as 340 Kelvin. So if you solve this expression, you will be able to calculate the value of Qt by AP. Now you know the Qt by AP due to HPC1, HC1C2 and then H of C2 to atmosphere. You take the average of all these values. This taking average, the Qt by AP average will be 753.209. So this is your Qt by AP value. Now from here you actually calculate what is your UT, that is the UT or UU, how much amount of the heat is the heat loss coefficient of the top side or upper side. So that is 753.209 divided by 425.5 minus 298, that comes around 5.907, and your UB, that is through your sides, that is that expression is your thermal insulation, that is your thermal conductivity of the insulation to that the thickness of your insulation. Let me write that. UB is KB divided by delta P. So this is the expression for UB. So your KB, that is as I said previously, that the thermal conductivity of the insulating material is only 0.04, and your delta B, that is the thickness of your thermal insulation, is 0.05 meter. So your UB will be 0.8, and we have seen that in the data in this particular, yes. Here as I said previously, the value of US is only 10% of UB. So 10% of UB will be 10% of 0.8. So what the amount of the heat loss coefficient through the side is only 10% of the heat loss coefficient that is happening of the bottom side. So 10% of 0.8 is 0.08. So if you add all these UT, UB and US, so as I told previously, the loss coefficient is not something that is particularly associated with one particular side. It is happening on all the sides, top side, sideways as well as bottom. So you have to take the sum of all the three. So UT plus UB plus US, so your UL value is 6.787. So you can actually see our assumption for the UT was actually 4. Now what we have got here is 6.787. So you can see actually the difference in the value of the loss coefficient. So this actually tells us that our assumption, whatever assumption we took for UL as well as for TC1 and TC2 are actually not that correct. So our assumptions can be told is that we have done wrong. Now we have to reiterate them. That is, you take another value of UL, another value of TC1 and TC2, and then do all the calculations once again and then check whether the UL value that you get at the end and the UL value that you have assumed at the beginning are same or not. So this is how usually we check for the accuracy of the calculation in case of any kind of equipment design within chemical engineering, and probably, I guess, if I am not wrong, within in other disciplines as well. So once you know that your value of UT is correct, like you assume another value of UT, you assume another value of TC1 and TC2, and then once you get to know that those values are correct, and the final what you calculated at the end and what you have assumed at the initial, if they both are same, then your calculations are, then you can consider that this is your final UTC and TC1 and TC2. So over there you can actually stop iterating your values, but till you get your UL assumed and UL calculated same, you have to keep reiterating the procedure. So let me write that, till you assumed, till UL assumed becomes equal to UL calculated, repeat the iterations. But since we do not have that much, I mean, this you can always do, if you can always do this reiteration yourself, but since we do not have that much amount of a time constraint, we consider that whatever values we have assumed are correct, and then we calculate the efficiency as well as that of the outlet temperature. So the efficiency, this is the important part of, at the end, like why we are actually solving is to calculate the efficiency of our flat plate collector system, which is nothing but the useful heat gain to the amount of heat that is absorbed by your, that is the radiant incident on the collector. So what is efficiency? Once again I am repeating, the useful heat gain to that of the radiation incident onto the collector. So QU by ITAC also can be taken, or it can be written as QU divided by SAP. So that value will be 2165.302 divided by IT, you calculated it as 2883 times AC, that is your area of the collector, which will be 1.76, because if you see the, where we have given the specification, if you see your area of the collector is 1.1 times 1.6, that will be 1.76, that will be your area. So if you calculate, your efficiency will be 2165, let me just write 2165 divided by 283 into 1.76, that is around 0.422. This into 100 will be your efficiency in terms of its percentage, so that is 42.66%. Efficiency is equal to 42.66%. This is how you calculate your efficiency. I guess apart from that, yes, you need to calculate what will be the outlet temperature of your fluid. That will be calculated by the expression. You take this value QU, I am going to calculate this here right in front. So QU is nothing but equal to MCP times T out minus T in of the fluid. This is basically the amount of heat transferred. What is basically the amount of heat is gained by the fluid through this process. So by knowing what will be the T out value, you can actually get an idea. of how much amount of the heat is actually transferred from the absorber plate to the fluid, and how much is actually the temperature, how much amount of, then this particular amount of heat what the fluid has gained has resulted in how much temperature increase. So Qu is 2165.302, this divided by m dot. M dot is your mass flow rate of the fluid that is flowing through your tubes, that is 100, divided by your Cp, that is 4.18, and here since it is given in terms of kg per hour, we are supposed to convert it into kg per second as standard SI unit, as I mentioned previously. Sorry, so Qu is equal to m, that is 100 divided by 3600 into 4.18 kilojoule per kg Kelvin, the value of Cp for water here we are taking, and T out is we are supposed to calculate minus T in. T in is the inlet temperature of the fluid, which is 60 degrees Celsius. So 358, 298 plus 60. So you can calculate the value of T out will come around so again I have to write one more step. .116, this is T out minus your 358. So if you calculate this, you will be getting your T out. That calculation I will leave it here because we do not have much time. So this week was specifically focused towards working on the problems related to the concentrating collectors, but since in the flat plate collector itself there was a specific part which was left out, we were unable to come to that particular portion. I thought we will come to that particular portion by 6 or 6:30, but it's fine. So till now what we have discussed is about a flat plate collector, that is your plate, the absorber plate is going to be a flat plate. It's a non-concentrating type of collector, but what happens over there is the amount of solar radiation that is absorbed by your surface may not be that high. The amount of solar radiation will be very less compared. So in order to harness more amount of the solar radiations from the sun, we go for concentrating type of collectors. So in case of concentrating type of collectors, you will have different kind of geometric arrangements, like one thing will be your spherical concentrating type and another one will be your cylindrical concentrating type. The reason why we use a concentrating type collectors is to increase the amount of solar radiation that is getting absorbed by the solar collector system. So primarily in our lecture, or what this particular course focuses is on your cylindrical parabolic concentrating solar collector system. So the problem solving will also be focused on cylindrical parabolic concentrating solar collector system. So similar question we will be dealing. It's just that there are certain parameters which will be different. So let me zoom out this so that the question is visible. I hope the question is visible now. So the question is, a cylindrical parabolic collector is installed on a building rooftop in Mumbai. Angle of this angle of 30 degrees pointing due south. Calculate the respective values on 16th August 14 hours late local apparent time. And it's also written your cylindrical parabolic collector works in mode 1. So in case of your flat plate collector, you actually do not have any kind of modes. In case of your concentrating solar collectors, you have different kinds of mode. The reason is, we have discussed even in week 2, as our earth rotates around the sun, so the amount of solar radiation that we will be harnessing from the sun will be different throughout the day. For example, in the morning, if you see, since the earth rotates around the sun will be in the east, but at 12 noon it will be on top of our forehead, and towards the evening it will set in the west direction. So we need to have a kind of a tracking system, a rotating collector system, so that at every part of the day we can harness maximum amount of radiation. So mode 1, what is actually meaning of the mode 1 is, you have a cylindrical parabolic collector which is basically rotating about its horizontal axis in the east and west direction. So if you consider this is east and west direction, you have your flat plate collector here, and that flat plate collector is rotating, you have your concentrating solar collector system. That concentrating solar collector system is actually rotating about its horizontal axis. That is the mode 1 of working mode 1. And your value of beam radiation is given as 725 watt per meter square. The reason why I am doing this question is because this question is something very similar to what you will be solving for assignment 4. If you see a assignment 4 question, now the last question is something that is specifically focused on what we are going to solve now. So with the rest amount of time we have in our bucket, we will be able to solve this question. So similar to flat plate collector, we have the specification for the adsorber tube, and then your concentrated data is given. So your length of your concentrator is 2m, your aperture, so it's a parabolic collector, so it will have a particular aperture that is around 3.6. Specular reflectivity, that is how much amount of the light, so the light actually falls on the parabolic collector and it gets reflected towards your receiver system. So so this is your parabolic collector. The radiations are going to fall on the parabolic collector and get reflected, and the receiver system will collect the reflected radiations. So that in order to measure that particular reflection radiation, we introduce a term called specular reflectivity. That particular value is 0.85. And intercept, the definition of intercept is the radiation reflected or refracted from the concentrator to the amount of radiation incident on to the collector. That is what is the intercept factor. So how much amount of your radiation is getting reflected from the concentrator to what is getting incident onto your the parabolic collector. So this value, the intercept value, will be always approximately close to 1, because majority of the amount of radiation that is falling, that is incident onto the parabolic collector, will get reflected, so that the receiver system can maximize the amount of solar radiation that it can absorb. So here we calculate the angle of incidence. Previously, if you see, the angle of incidence was a very big formula with cos theta, cos phi, cos delta, cos omega, and there were a lot of terms present in the expression. Let me just show that once again. If you see here, the angle of incidence is a function of sine phi, sine delta, cos beta, cos omega, cos gamma. It's approximately a function of 5 different solar angles, but here it's just dealing with delta, that is your declination angle, and omega, that is your hour angle. Here we know both, since we have considered August 16, so your delta value will be 13.45 and omega is your hour angle. Here we have taken 14 hours, so 14 hours will be minus 30 degree Celsius. So this is how you calculate the value of cos theta I. Let me zoom in. So cos theta I is sin square delta plus cos square delta times cos omega. So if you substitute, it will be 0.872. So sine of 13.54, 0.23 plus 0.0529, and we take the cos 0.972, 0.972 square, 0.944 into cos of 30, into cos 30 will be 0.5. Oh no, cos 30 is 0.866. This, and you actually add this with 0.871. Okay, the value will be, let me just check in my calculator. Point 0.872 or the exact value is 0.87336. I have taken 0.872. So your theta I will be 29.27 degrees. Now you know your angle of incidence, and once you know the angle of incidence, that is going to, the beam has got reflected and then is actually taken up by your receiver. So the angle of incidence at your receiver is 29.27. Your receiver will indeed have your transparent glass cover, absorber plate, and then your fluid tubes, because that is what is going to take up the useful heat gain for your applications. So you need to actually repeat the procedure. So you need to, so since the light is going to get incident onto the transparent glass cover, it will undergo refraction. So similar to what we have done yesterday, or what we actually saw today also, you need to calculate the value of theta r, rho 1, rho 2, tau r1, tau r2, tau r, tau alpha, and tau, and the tau alpha b. The reason why here, but here we actually do not calculate the value of tau alpha d. The reason is because in case of your concentrating solar collectors, we only focus on beam radiation. There will be diffusive radiation that will be falling onto your concentrating collector, but majority of the radiation what is going to be used up for your application purpose will be only your beam radiation. So here it will be sufficient if you calculate only the value of tau alpha b. Oh, you want me to say? Yeah. In case of your flat plate collector, both your beam radiation as well as your diffusive radiation will be falling onto your flat plate collector. But in case of concentrating solar collector, it will be only your beam radiation. Here you do not actually need to calculate the value of tau alpha d. For example, if you remember, in the initial phase of this today's session, we calculated the value of tau alpha d also. We saw what will be the value of tau alpha d here. So we assume the value of theta r as 60, theta I as 60, calculated the angle of refraction for that diffusive beam that is going through the glass cover, and then we calculated tau alpha d. but in case of your concentrating solar collector, it is only your beam radiation that you have to focus. So here we have taken tau alpha B value and we get it as 0.7877. You actually need to follow the entirely the same process, but one different thing is here the number of glass cover system we have taken as 1. Let me just mention that. So yeah. I guess this is this week 4's question, right? Actually, I have told you the concept. I'm not supposed to actually say the answer. So anyway, I have told it. I have actually revealed the answer in my explanation as such. So you will be able to now know what is the answer for that question. So here, while calculating our tau r and tau alpha, our rho 1 and rho 2, that is the polarization component due to reflection and refraction, here we have assumed it as the number of covers, glass cover is 1. Let me just write it if it is not. Number of glass cover, that is your transparent glass cover, is equal to 1. So since it is 1, your formula for tau r1 is nothing but 1 minus rho 1 divided by 1 plus rho 1, and your tau r2 will be 1 minus rho 2 divided by 1 plus rho 2. I guess if you can actually remember this formula, so that it will be easy even if the number of glass covers that is being used in your solar collector system is more. So the general formula is tau r is equal tau r1 is equal to 1 minus rho 1 divided by 1 plus 2m minus 1 times rho 1. So your m is the number of glass covers. So in the previous problem we had totally 2 glass covers, so your m value was 2. So 2 into 2 4 and minus 1 was 3. So that is the reason here if you see, we have used the value 3, whereas in our case now we have assumed the number of glass covers, that is what we have taken is the number of glass covers is 1. So 2 into 1 will be 1, 2 minus 1 is 1. So you can remember this general formula, so that it will be easy. 1 minus rho 2 divided by 1 plus 2m minus 1 times rho 2. Yeah, these two are the formulas. So once you know tau r1 and tau r2, your tau r is tau r1 plus tau r2 divided by 2. Tau r is tau r1 plus tau r2 divided by 2. Tau alpha you calculate from your Boyger's law, that is e power minus k delta c by cos theta r. Once you know tau alpha, tau r, you can calculate the transmissivity tau, which is tau alpha into tau r. Once you know the value of tau, tau alpha b is as in the same way. Tau alpha based on your beam radiation will be equal to tau alpha, that is your absorptivity of your plate, divided by 1 minus alpha p into rho d. Rho d is nothing but your diffusive reflectivity, which the value for which you can take it as 0.2. So you calculate your value of tau alpha b. Now Our question is, we are supposed to calculate what will be the solar radiation that will be incident onto your receiver system of the uh, cylindrical parabolic solar collector system, which is given by this expression. S is equal to, you can take down this expression, S is equal to IBRB E nu tau alpha B plus IBRB into tau alpha B times D naught minus W minus D naught. IB is your intensity of the instantaneous beam radiation. RB is nothing but tilt factor for your beam radiation. E is specular reflectivity. Gamma is your intercept factor, that is the radiation that gets reflected or refracted towards to the amount of radiation that is incident onto your collector. Tau alpha B is your transmissivity absorptivity product based on beam radiation, and your D naught is nothing but the outer diameter of the tube. W is your aperture width, that is you have a parabolic collector, so for that you will have a particular aperture which is denoted by W minus D naught. IB, if you see in the question, I have taken the value of IB as 725. So you know your value of IB. RB is 1. RB is nothing but the tilt factor for beam radiation, which is equal to cos theta I divided by theta, let me write cos O. I will modify all these things in the PPT that will be uploaded by today or by tomorrow, divided by cos of theta z. Theta z is nothing but your zenith angle, which you actually know. Yesterday also we saw zenith angle is nothing but the formula sin phi sin delta plus cos phi cos delta cos omega. Your value of RB will be around 1 if you calculate. Tau alpha B you have calculated in the previous slide and the value was around 0.787, and your specular reflectivity and your intercept factor is given in the question, 0.85 and 0.95. So you have this particular part of the expression is done. Now you come to this D naught minus W minus D naught. D naught is outer diameter of your tube, that is 0.036 meter, and your W is the aperture of the concentrator, that is 3.6 meters. So if you calculate, your S will be 473.083 watt per meter square. So this, by solving this question, you will be now actually knowing how to solve the assignment problem question, because if you see in the assignment problem question, it's just that the values are different, but the questions are actually the same. Calculating of incident angle, zenith angle, the solar flux that is absorbed by your collector system. So those are approximately the same questions which we have discussed here. So you will be easily able to solve. It's just that you need to plug in your values according to the questions. So in case if you have so the today's live session ends here. In case if you have any doubt, you can let me know now. And I also wanted to know, is this kind of problem solving actually helpful? Because if you see the last question, that is something relevant to what you are actually going to solve for your assignment, but the third part of the question that we took yesterday for the week 3 live interaction session was quite tedious and was more specialized or focused towards the heat transfer aspect. So are you okay with solving those kind of questions, or shall we just not like work too much towards those? Because those are quite tedious calculations also, and there are many terms for which you actually need to know the meaning, like Rayleigh number, what is Rayleigh number, what is Nusselt number. It's just given the expression is HL by K or H into delta PC or delta C1 C2 by K, but what it actually means, what is the meaning of the Nusselt number? It is basically defined as the ratio of the convective heat transfer resistance, conductive heat transfer resistance to the convective heat transfer resistance. Knowing that what those terms actually mean, what is the difference between Rayleigh and Nusselt number, and those are all kind of very chemical engineering oriented or something that is specifically uh, focused on heat transfer aspects of the course. So do let me know, are you guys okay with solving those type of questions now, or you can also write it in the chat box. Anybody, like any kind of feedback that you want to give, like based on the slides, is it okay, or should we need to improve on something else, or what, the kind of question, it is okay, like I mean the slide, and I mean the pace at the pace of explanation is also, I mean, do I need to slow up, or it's okay? So okay, then that's fine. So now hopefully after this particular discussion you will be able to solve for the week 4 assignment, I guess. Only the thing that I haven't discussed about is the concentration ratios, which is nothing but the effective area of your aperture to the surface area of the absorber. So you have many different kinds of concentrating solar collector systems. So depending upon those, the value of the concentrating ratio, that is the effective area of the aperture or the average flux received by your receiver to the flux over the aperture, those values, it will be easily available in the presentation. If you go through your video lectures, then totally 8 different kinds of concentrating solar collector system design has been explained, and from there you will be able to actually get to know what are the values of the concentrating ratio. And here we have actually solved the problem, and the problem that you are going to solve for week 4 is also of a similar type. So once this video gets uploaded, I'll try to upload it very soon, you will be able to solve that question, I hope, comfortably. So in case if anybody has no doubts, okay, yeah, before that, if you see in the ask a question tab, there were few questions raised about the answer case, like the answer what you guys have given and then the answer is not actually matching. One of the reasons why the answer is actually not matching is because you need to be quite more rigorous in the calculation aspect. You have to, for every single parameter that you calculate, it is better to take approximately 5 decimal places. Like let's say it's 0.75, you can take 0.7543, whatever that value you are getting, take up to 5 decimal places and take your value of rho d as 0.2, and if you do that, then your answer and then the answer key will exactly match. Because I have solved, since we do not have time for today, we won't be able to see that question. So next week, before we start for the week 5 session, we will actually take up that question and then solve it, like literally multiplying and doing all the mathematical calculation in the live session before we proceed for the content that is focused for week 5. So if nobody has any doubt, then let me stop presenting. Yeah, so let me formally conclude the session. So thank you for joining today for the week 4 live interaction session for the course Renewable Energy Engineering, Solar, Wind and Biomass Energy System. So in case if you guys have any doubts, please write to me. My email ID is actually given in the presentation. I'll try to respond to your queries as soon as possible, or you can also utilize the ask a question platform. If you go to your NPTEL portal, in the header section you will actually find ask a question platform. You can also submit your questions there. Either me or the other NPTEL TAs will be answering to your questions very soon. And so I would like to thank the course instructors as well as the NPTEL team for giving me this opportunity to interact with you on this Sunday evening from 5 p.m. to 7 p.m. Through this platform. And we will meet for week 5 live interaction session on 24th February Sunday, same 5 to 7 p.m. in the evening. So till then, thank you for joining today, and yeah, so we can conclude the session. Bye.